Hello everybody. So in this short video, we'll be discussing about stereochemistry problem solving one. So this is one problem we have given last week, and many of you asked to discuss about the solution. So I'll be discussing here in this small short video for our first year theory class. So the question was the Feist acid has molecular formula C6H6O4 and is a cyclopropane based natural product. It is optically active and has one symmetry element present within the molecule. Predict its structure. Okay, so we'll discuss on problem solving perspective, considering one has minimum required basic knowledge. Okay, let us proceed with the problem. So before going in details, what we'll be discussing first about double bond equivalent or level of unsaturation calculator. Okay, how to calculate the means double bond equivalent. So double bond equivalent equal to number of tetravalent atom present in the molecule plus number of trivalent atom present. Let's say you have a two nitrogen atoms, it will be 2 by 2 always, minus number of monovalent atom present by 2 plus 1. So what are the tetravalent atom possible? It can be carbon, silicon. It can, what will be trivalent? It can be nitrogen, mostly we will focus. However, phosphorus can also be trivalent like nitrogen. And number of monovalent atom. So these monovalent atoms are like hydrogen, halogens like uh, fluorine, chlorine, bromine, iodine, all are possible. Okay. So one double bond equal to one ring or one double bond. Two double bonds can be, two double bond equivalent can be two rings. Okay, two double bonds or one triple bond. Also one ring plus one double bond. Like this, all the possible combination we can discuss. Okay. So example, benzene ring has four double bond equivalent because it is a cyclic, so it has a cyclic molecule. It has one ring and it has a three double bond. However, you know that all the double bond or pi electron are conjugated, so delocalized. We cannot really localize like a one double bond, one single bond alternative. However, just for our discussion, we are thinking like this. Okay, we're discussing like this four double bond equivalent. So for our purpose, we will consider like a number of carbon plus nitrogen, number of nitrogen atom by 2, or monovalent hydrogen minus hydrogen by 2 minus number of halogen atom by 2, like this plus 1. So if you consider our Feist acid, which has molecular formula C6H6O4, so 6 tetravalent atom present minus the monovalent atom, the hydrogen only here, so 6 hydrogen atom by 2 plus 1, it comes around 4. Okay, if you have this, now let us discuss what are the characteristic present in the molecule. Okay, so in the molecule, if you consider, it has a double bond equivalent 4 and it is a cyclopropane based natural product. So cyclopropane ring equivalent to one double bond goes there out of 4, and it has acid. Okay, so one carboxylic acid, if you consider, it will be one double bond equivalent. Okay, and if you have two, it will be two double bond equivalent. If you have three carboxylic acid functional group, it will be three. So like this. So it is a chiral, so it cannot be, we have to only get the chiral molecule. It cannot even be meso. Okay, has one symmetry element, so it is actually optically active. So it will be chiral. So one symmetry element present. So what are the symmetry element possible in a molecule? Still molecule will be chiral. So that is, this has to be C2 symmetric axis. Okay. Uh, Now let us think about the possibility. What are the possibles? Okay, all should be the acid, right? Because the problem is so that is Feist acid. And if you know, it is a very interesting. Only having 6 number of carbons, C6H6O4, and you can see that only considering the acid, so many possibilities are there, right, for this molecule. Okay, if you don't have acid, several other will come. So this is the beauty of organic chemistry. So with a simple molecular formula, even you can generate so many beautiful molecules having different properties, having different bond connectivity. So many isomers are possible. Okay, so if you start with this one, having two carboxylic acid attached on the same carbon, so it is a achiral molecule. So this is not the our answer. If you consider another one, so this double bond you just isomerize to here. So this molecule, this is also a chiral, and if you consider one carboxylic acid and this methyl goes there like ester, this acid and ester together present on the same carbon, so this is also a chiral molecule. If you have this ester group coming there, then this is a chiral molecule, but it has no symmetry element. Okay, so this is also not our answer, but this is chiral, right? And if you consider a par acid, which is also acid for our sake of argument and having one aldehyde group there, so this is also chiral but has no symmetry element. You have also possibility this carboxylic acid group comes from there to there, so it can be also chiral but it has no symmetry element, and it can also present in two form, okay, in geometrical isomer, right? So this is really interesting, just by switching a little bit and you can generate so many beautiful molecules. So the finally is this one, okay, and you know this has a C6 H8O4 and double bond equivalent 3, but we have 4. So two hydrogen has to go away. So how you can remove these two hydrogen, how many way possible, and we'll see whether that fits our answer or not. In that way, what we'll be doing, if you take this carboxylic acid here, or dicarboxylic acid, and you remove two hydrogen across these two carbon, okay, you get this alkene. Is this molecule chiral? No, this is not chiral, so this is achiral. This is not our answer. Now let's switch to the next possibility. So if you have this double bond here, exocyclic, and you have a two carboxylic acid which is cis in geometry, cis dicarboxylic acid substitutions has plane of symmetry which is denoted as sigma. So it is a meso compound despite having two chiral center, okay, because it has a symmetry element present within the molecule, and so it is a meso compound, and this is also not our answer. You know the mesotartaric acid, right? The similar way. So this is another possibility. So if you just move this double bond here to there, so this is also chiral, and when a chiral molecule you are considering, it has to have pair of enantiomer. So basically you have to draw these two structure, both are enantiomer to each other. In that way it has, but this molecule has no symmetry. So this has no symmetry, but both the enantiomer are possible. It is existing as a pair of enantiomer, and it is a strained molecule. Okay, I'll discuss in a few minutes. Okay, so this is not the Feist acid, because in Feist acid what we discussed, it has a symmetry element. So the final one, if you consider just this molecule which is cis, if you make it a trans, so in this case this is a chiral molecule and it has a C2 rotational axis, this C2 symmetry element. Same way this is also enantiomer of this molecule, so this also present as a pair of enantiomer. Okay, so you don't know which one is natural, right? So for you difficult, but if these two are the possible answer at this point. So one it has C2 rotational axis, both are possible, both the enantiomer, a pair of enantiomers, and this is your Feist acid. So this is your answer. Now you know for sp3 hybridized orbital, okay, why this molecule is strained and this is naturally occurring. Maybe one of the reason, this molecule, it is if you consider tetrahedral carbon sp3 hybridized, it has bond angle 109.5, which is here. Okay, and if you make it a sp2 hybridized like this, these two cases, so here and this case and here in this case, so this will be like ideally it should be 120 degrees. So now for the triangle, if you consider ideally for this case, let's say all are, let assume all these edges are equal. Okay, so for the equilateral triangle has three equal angle, and it will be each angle will be 60 degrees. So deviation from 120 to 60 is more, or 100.925 to 60 is more, obviously. So 120 to 60 is more deviation, so it want to minimize this deviation, so the double bond goes in the exo. This can be possibly one explanation. This is more comparatively more stable than your this molecule. So this Feist acid present in nature in this form. Okay, and I hope you convinced with this answer, and thank you very much for watching this video. We'll see whether we can make more videos on the problem solving. Thank you.